Okay, cool. Cool. Yeah, welcome. My name is Alex. I'm a software engineer at Dropbox, and today I will be presenting. Oh gosh, there we go. Okay. Yeah, I'm going to present about our build systems. We only have half an hour for that one, so I'm not gonna lie. I'm going to be pretty concise today. Yeah, but before we begin, my name is Alex. I'm the tech lead for Build Toolchains team at Dropbox for a year now. And yeah, so the current agenda is I'll start with 101 crash course on Bazel. So I realized that probably not everyone here is using Bazel at work. Okay, does anyone use Bazel at work right now? Raise your hand. Okay, cool. Yeah, so that's why we're going to start with a crash course, and then I'm going to tell you a bit more about our current setup, the continuous integration systems, the remote cache, and also about the issues we're seeing in production right now, and what are we doing to solve them. You know, what's the vision and what we plan to do going forward, and then I'll share a few closing thoughts after working with those systems for quite some time now, and we'll close out in a Q&A. So I guess the presentation is probably going to be like even shorter than 30 minutes because we want to have a Q&A. Cool. So first of all, what is Bazel? So Bazel is a generic purpose build system. When I'm saying generic purpose, I mean it's not tied to a specific language or ecosystem. So if you guys are like, I don't know, writing Java, you might be used to Maven. If you're writing Golang, then you know there's like Go build and all of that. If you're writing Rust, there's Cargo. If you're writing JavaScript, then you probably use NPM, Yarn, or any other stuff. Bazel is generic purpose in that sense that you know it's not tied to any specific ecosystem, but can be used with any of those languages. I think what's also very important is that it's a declarative build system in the sense that you don't really write scripts that build something as much as you declare targets and dependencies between them, right? So essentially you're building a structure about like what you want to build, and then Bazel figures out the rest. One thing I really like about Bazel when I was picking it up is that in my opinion it has a low entry barrier. So like it's pretty simple to start building something with Bazel. To be honest, the ceiling of things you can learn about Bazel is pretty high, but like to start doing something, I think it's actually pretty simple to start. So I think that's pretty cool. Yeah, so that's more or less how a build file looks in Bazel. There's a build file that you put next to your sources, and you essentially declare what we call targets. So target is essentially like one of those that you can see, like hello greet is a target, hello world is a target, and you know it's of a specific type. So the type is like CC library or CC binary in that case. You declare some sources, you declare the dependencies, and what internally Bazel does, like it forms this kind of a target dependency graph. So at first we've got like the source file, so you've got like you know hello world, hello greet, blah 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 blah. Then you've got like the library target, which you know takes the sources, and then it's being part of the dependencies for the hello world. So essentially, like that's how Bazel like thinks in terms of building, in terms of graphs and like dependencies between things. So, but 101, like how do you use Bazel, right? So you essentially create a build file, like I just shown, like you type some stuff, like say, okay, I want to build some, I don't know, C++ binary or Go binary or wherever. You essentially then write Bazel build path to your code directory and the rule name, and then essentially Bazel is going to figure out the rest. So in that case, if I go back here, then essentially that will like path to something something colon hello world, right? And then Bazel knows to build that particular binary. And essentially that's kind of it. Like at this point, like Bazel is going to like first find out what has to be built, like you know if there's like any transitive dependencies. If there are, it's going to build them, you know, and it's going to essentially scan the whole graph for you. So as long as you've got like the rule implementations, so by rule implementations I mean again going back would be CC library and CC binary. As long as those are like provided to you, that's all you have to do. And that's more or less how like the output looks like. you just write it like it builds. It's going to show you like the output. So in that case, that's like Bazel bin/a.out. So that's a binary file that I just built, and and then you can do whatever you want with it. So a bit of a how do I say that? Definitions, if you will. So first of all, like Bazel is an artifact-first system. So what it means that when you type Bazel build, it's essentially trying to say, okay, I need those artifacts and I need to provide them to the user, and it's going to figure out how to get them, right? So again, for all the stuff around the build graph. An important thing to note is like a target can have multiple actions, okay? So an action is like the smallest unit of work Bazel can do, and you can think of it as a single command that has to be run in order to progress the build forward. So, I don't know, that would be, I don't know, call C++ compiler to compile a file, or like invoke a linker to build a binary, or, I don't know, invoke some sort of a tool, right? So it's like the smallest thing that Bazel is doing, and it essentially is just invoking an external thing to, to do something. And yeah, basically what you have is like, you've got inputs, you've got an action, and then from this action you've got some outputs, which are like, the result of a state command. Yeah, so that's like, like the 101. I know it's very short and concise, but again, we don't have that much time. But that's generally like what 80% of Bazel users do. Like that's the only thing they really have to do, which I think is pretty neat. So I'm going to talk a bit more about like the Dropbox setup right now. So we run our own CI system called Changes. It supports multiple CI workflows, but like the most important one by far is building Bazel builds. So, essentially we schedule a pod into our cluster, and that one is invoking Bazel build. We run a few separate microservices to aid with that. So for instance, we run something called Bazel Query Service for another thing that Bazel can do, which is Bazel Query, which is pretty nice. And Bazel Query is essentially allowing you to query for information about your build graph, right? So essentially, it can answer questions like, what targets depend on the source file? Like, I don't know, what tests do I have to run if I change the source file, which is very useful. This is how we determine which tests have to be rerun if you essentially change a source file. And also a very important thing to know about our CI is that we short the workflow. So, if a change, triggers 10,000 tests, which can happen, then essentially we're going to shard it across multiple pods in order to, parallelize the work. So I believe that's the graph, yeah. So that's more or less like a very high level, architecture diagram. You've got a client which sends a request to a scheduler inside the CI. It multiplies it into multiple shards, and each of a shard essentially runs Bazel build, test targets, it builds the test, rebuilds whatever needs to be rebuilt, and then runs Bazel test to invoke the test, because, Bazel supports that as well. So yeah, one important thing to remember is that Bazel, so Bazel, first of all, has originated back from Google, right? So this is what Google uses internally for their monorepo, and since Dropbox operates a monorepo as well, it's a pretty good fit for us. And how it works is essentially we mount a Git repository inside our pods and CI, and then essentially that's how we can do a Bazel build or Bazel test on the same monorepo. And very important thing to remember is that not all code is being built, because one of the most important features of Bazel is that because you are running essentially you're walking a graph, right, of actions, all of this can be cached, right? So essentially, if an action has been run before, you can cache it. And we do not rebuild things from ground up, which speeds up things dramatically. I think that without cache, we wouldn't be able to build that much stuff. A typical CI job is 90% just cache hits. So essentially it's just oh, that has been built, oh, that has been built, oh, that has been built. And it only essentially rebuilds stuff which is new code. which is very, very useful because like, when you're running like a very big repo, essentially it's like infeasible to like build stuff from ground up. And yeah, essentially what happens at the end is like when CI finishes the job, like all the actions that have been built before that haven't been in the cache are going to be uploaded to the cache so that other builds and other clients can use it in the future. Okay. Okay, let's go forward. Cool. Yeah, so I told you a bit more about the CI, and now I'm going to tell a bit more about our developer machines. So each of us has a laptop, but we do not typically develop on them. Well, some people do, but I do not. And we have something like a Dropbox, which is like a Linux instance where you can have your own repo and build stuff, and it's much more beefy than the laptop and stuff like that. So we've got a typical like clone Git mono repo. We pull it to the machine, and again we're using Bazel and we're using the cache as well. So developers do not have to rebuild the whole thing from ground up. They are using the cache, and basically that's why like the build is much very The important thing is about the cache that is being used by developers that it's read-only. So like developers that write new code cannot write to the cache, and that's a security measurement because like in case like a developer would be like compromised, they could potentially upload malicious artifacts to the cache, which is something we wouldn't want. So what happens is essentially if a CI populates the cache, and that's how other developers can reuse the artifacts that have been rebuilt previously. And that's why the hit ratio on the read-only caches is much higher. Like I think it's 99% or so last time I checked our metrics. So like developers basically don't build code except for stuff they actually change, which I think is pretty neat. Cool. Yeah, that's more or less the setup that we run for developer machines. So you've got the client, which is the user. It sends a build request. Bazel checks the cache, but the important thing to mention is that we run a machine cache that developers have locally, right? Because I mentioned, okay, they cannot write to the distributed cache we have, but they have their own on-machine local cache instance, and that one is actually like they can write to it. So that way, like they can maintain like high cache hit ratios on things that they themselves written and modified, without like exposing all the other people in the company to like potential problems. And essentially, what happens like if a Bazel sees a cache miss inside this on-machine cache, then it's essentially proxied to the distributed service that we run. Cool. Yeah, so a bit more about the remote cache setup. I know I'm talking a lot about this, but I think it's important. So yeah, they're running an L1 on-machine cache, and also an important thing is that the CI does very same. Like they also have like a per machine cache, and it's pretty important because like when you got like a CI machine, right? Let's say, I don't know, 100 cores or wherever, you've got like multiple Kubernetes pods allocated on this one. You want to be able to reuse the cache between pods on that machine, right? So our CI does a few small things in order to like allocate similar work on same machines, and then we can benefit from that cache locality, right? And that's why we run this local cache on CI machines as well. And then we've got the L2 per metro, so per metro, like per data center to be precise. So we've got like a few data centers we replicate to, and like each of them are like separate. And then we've got like another distributed blob cache service that's like our persistence layer. So that's like the L3 and final layer of caching. So it looks more or less like this, right? So I know I'm probably going to reiterate what I just said, but there's like a CA build short, there's like a local machine cache. Same for the dev boxes. If cache misses are seen, then it goes to the metro cache, which it's like essentially a distributed service. And then if that misses, then we go to like the outer globally replicated blob store cache. And another important thing to mention about those caches is like you can like approach this problem like from multiple sides. You could like either shard it. So if you've got like 10 machines, you could allocate like parts of a key space to each of a machine, but we don't do that. We do replicate all of the blobs on each of the machines because like we're trying to essentially scale the read rate, which is like much higher than the write rate that this cache sees. So that's why it's not sharded. Cool. Yeah, so I know it's fast and very high level, but that's more or less how it looks like right now. And now I'm going to talk a bit more about the issues. So like, you know, this is not perfect, and actually it has quite a few problems right now. So my team is one of those teams that tries to solve those problems. Yeah, so the first problem that you're going to see if you like, let's say you join Dropbox and you start running, like you're going to see like if you measure how much network transfer you have on your like machine when you're building something, it's a lot. And the problem is that essentially you are doing cache fetches for every artifact inside the tree, right? So let's say if you've got, I don't know, 10 libraries and then a binary that depends on those 10 libraries, Bazel is going to fetch all those libraries from the cache and then fetch the binary, even though you are typically only interested in the binary itself. This is a problem that's caused by like historical like, nature. Like Bazel, essentially that's how it worked, right? And then they added the caching. So, you know, they just had no easy way to solve this problem. So that's how it kind of stayed by default. And because of that, like you just fetch too many things from the cache. And that, you know, just doesn't make much sense. So essentially if we look at this graph, like essentially all of this is going to be downloaded from the cache, even if you care just about the end result. So what do? So to address this problem, Google has created a feature called build without the bytes, which is a very fancy name for just not downloading that many things. So build without the bytes essentially means that you can specify whether you're interested in the whole build graph, which is cool. You maybe are interested in only the top level artifacts. So let's say if you're building a binary, you are saying, okay, if you're running into cache hits, please fetch only the binary and do not download the rest. Or you could even do remote download minimal, which means that do not download anything, just build stuff, but do not download anything from the cache if you've got any cache hits, which can be sometimes useful. So we actually worked a lot on like adopting this because it sounds pretty simple, but comes with a few interesting invariants about what the cache has to hold. And but it's pretty useful in terms of like end-to-end waiting times on like heavily cache builds, which is like the majority of builds that Dropbox does. So like the current estimate that I was looking into was that it's around 30% on the fully cache build. So like if a build takes like 100 seconds, then instead of that, it's 70 seconds, just because you do not have to fetch that many things from the cache. So we adopted this for DevBox environments, I believe 3 months back, and we saw those gains come. There is still some room for improvement because of how, well, it's a legacy thing essentially in a repository. There are like some rules which are kind of abusing Bazel, and because of that, like they kind of break this feature, but we still see like 15% reduction in build times, which was pretty cool. And we still didn't adopt this for the CI, but we're about to do so in 2024. So that's one big problem. Yeah, another even bigger problem is that the CI setup that they've shown you is essentially memory bound. What does it mean? It essentially means that if you look at any given moment inside our CI, you will see that amount of memory reserved from the machines is close to 100%, but the amount of like CPU reserved, not to mention the usage, is like, it's much lower. I'm not going to give an exact number, but it's much lower. So what's the problem? The problem is that the pod is long-lived, right? Like you gotta build everything, like, I know, 100 tests, you've got to run all of those tests. And like the memory usage is going to vary, depending on what you're running, right? So I know if there's like one command in the build graph that I know needs like a lot of memory, then it's going to be like very high, and then it's going to go down, and then maybe it stays down for another 10 minutes. So the problem is that this a lot of times memory over time is being wasted by the pods, right? And because of that, we cannot schedule enough pods. And if we cannot schedule enough pods, we're underutilizing our CPUs, right? And that's why like we're just not running to the full potential, right? We're not running to the full potential of our own cluster. So I created this graph which kind of summarizes the problem, right? So the green line is like the actual usage, and the yellow line is you know, the reservation that the pod has inside the Kubernetes cluster. And unfortunately, we do not run vertical autoscaling on the pods. So, you know, essentially all of this like area between yellow and green line is waste that could be used for other pods and, you know, for utilizing the resources on the machine better. So how do we plan to solve that? So essentially, you know, the build community around Bazel, but not only Bazel, also around Bug, Pants, and other build systems that are coming up right now, are focusing around this thing called remote execution, right? So there has been a protocol built by Google, originally for Bazel, but now it's like a bit more of a generic thing, which essentially means it's a protocol for building stuff somewhere else than the client, right? So if you've got like a Bazel client, instead of building stuff locally, you're asking a distributed service to do it for you. So it's very, very simple. Like it has like one method, like an execute request. You upload the inputs and you ask it to execute, and you just download the outputs if you're interested in those. So the important thing is that remote execution deals with an action, right? So the action, as I mentioned before, is like the smallest unit of work Bazel has. So that's like just literally one command. So what it means is that even like if a command, you know, takes a lot of memory, right, or needs a lot of CPU, you allocate a worker, you put it there, but you know it finishes after, I don't know, 10 seconds, let's say, and then the worker is free, and you can use those resources again for allocation. So because of this like much more granular like way of allocating work, we can be much smarter about like how we pack the work on the machines, and because of that, we can get around the problem that we saw on the previous slides. Another, I think, a big benefit actually is that like, you know, we are moving away from like our bespoke solution towards like a industry standard solution that's being adopted. So, you know, reducing like this in-house surface for us is also very important in terms of like other projects that that we have in developer productivity space. So that's like a general like graph of like how it works. So, you know, you've got a Bazel client. It uploads the input. So I know if you change a source code file, you have to upload it. You ask the service to execute it, and then you typically have like multiple sizes of workers, and the work is allocated to a worker. You know, the command is being run, the outputs are being uploaded to the cache, and then the success is being returned to the client. And then the client can just download the output from the cache if they need to, right? So that's how you distribute your build instead of doing this locally. Cool. Yeah, I rushed through it, but yeah, I just wanted to have like a few closing thoughts. Let me just see, like, what's the time? Okay, yeah, I'm probably late a bit, but what I want to say about Bazel is that it's pretty cool, but it has a cost of adoption. Like, if you really want to use all of those things, you need to have this remote cache. If you want to have a remote execution service, then you have to support it. It can be non-trivial to debug, especially when builds are non-deterministic. Like, you know, if you build the same thing and it gives you different outputs, then it essentially is going to break the cache because like the hashes are not going to match. So, you know, tracing those can be challenging. This has been especially prevalent with Java builds, which really like to put like timestamps and stuff like that into the builds. So finding out what's trashing the cache can be a problem. And I think I wouldn't recommend Bazel to people who are writing a single ecosystem, right? So if your company or like a project or wherever, it's just one like, you know, Golang or just Java or just like C++ or wherever, it probably doesn't make sense because like I'd say if you're in one ecosystem, it's good to stay within it. But if you're already at a place where you need to scale out the builds, you need to use all of those features around like performance and caching, and you've got multiple ecosystems mixed, right, which happens to large companies like Dropbox, then Bazel is worth a try. Cool. That being said, I think I'm done. So we can have a quick Q&A now.
All right. Thank you very much for the speech. Look, guys, do you have any questions? Now is the time.
I'm not sure who raised their hand first.
First question, how
Yeah.
do you, because you know, cache invalidation is the most difficult thing in the computer science, as you
Sure.
know, as
Sure.
we all know. So there are probably multiple factors you take in
Yeah.
calculating the hashes. Could you tell a little bit more about that?
Yeah.
Because it's not the
Yeah.
not only the source code, because
Sure.
that's just
So,
one factor.
so essentially what happens that like remote cache has two types of blobs. One called cast blobs, which is content addressable storage, which essentially is keyed by the SHA hash of the content, right? So essentially like you've got SHA key of some content, and then by that key you can get the content. And then you've got the AC cache, which is essentially action cache, right? And how the cache for that one is built is essentially taking the hash of a command, taking all the hashes of the inputs and builds a Merkle tree for that. And that's how all of this combined builds an action digest, which is used to keep the action. So if one of the inputs changes, command changes, any of the dependencies changes, the action digest is going to change, and that's how the system knows that it has to be rebuilt. Does that answer your question? You can, Bazel supports a concept of platforms, so you can have multiple platforms, and again, this is part of like all of this calculation, so essentially like, you know, it doesn't really matter.
Thank you. Please raise your hands. Who is next?
Hi. It doesn't work?
You talk about better utilization of the nodes.
Yeah.
And I have a question. Did you have any idea how to deal with garbage collector languages where you cannot just calculate memory that will be used? You plan to still have overhead, or there is some better strategy?
In terms of like execution of stuff, like
Because
yeah.
In garbage collector languages, it happens that it's not always at the same time the memory free is executed, so it sometimes happens 1 of 10 builds is going above the memory limit.
Yeah, that's true. Yeah, so essentially like for current setup, like the CI, again, we allocate for the peak requirement. So, you know, it uses whatever memory it has on the pod. If it goes out of memory, then pod goes out of memory. And, you know, essentially then we're like, oh, we have to bump like the memory usage of those pods. In remote execution, we are trying to be smarter about this. So we run multiple sizes of workers, and we're trying to right size the work into a specific worker. So one of the systems I'm trialing right now essentially is running, like, it tries to run on like multiple sizes of workers and tries to see, okay, this one is too small, it goes out of memory, but this one is big enough. So in the future, I'm going to allocate for this big worker, right? So essentially, that's how we plan to do. Like, you've got like multiple sizes of workers, and eventually we converge to the right size of a worker that satisfies the right requirements in terms of like memory, right? So what you mentioned, but also like whether like the work parallelizes well. So for instance, like we do things like, okay, we run this on one CPU worker and it runs in 2 seconds. And if I do it on a 4-core machine, it's still 2 seconds. So it makes no sense to allocate on a 4 CPU machine. We are going to allocate on one CPU and use the free CPU for other things. But for instance, if you've got like something which parallelizes very well, so C++ compilers are a very good example of that, then essentially we're going to allocate on the workers which have multiple CPUs to take, you know, to use that parallelization. And spoiler alert, Python compilers are not parallelizing well.
I have a question about the caching system. Does
about what? Sorry?
Caching system.
Yeah.
Does Bazel support like Redis or memcached, or?
Yeah. So essentially, like it's a specific protocol you have to follow, but like the persistence layer you're using is up to you. So we essentially our cache is adhering to the protocol, but behind it you can put whatever you want. So in our case, we use our own in-house blob store, which is not Redis, but if you want to, there's absolutely no problem using Redis at all. In fact, many implementations of remote cache that you're going to find in the internet do support Redis as the cache backend. But,
Okay.
But you still need something that translates the remote cache protocol calls into the Redis calls. And I see that there has been...
Yeah, and one more question.
Go on.
So Python is not used greatly with Bazel because it does
Yeah.
not support
We built all of our Python with Bazel.
in Bazel.
Yeah,
Okay.
because like you can invoke all the necessary compilers and tools via Bazel, right? Like you've got a Python toolchain and essentially all of this is supported. Like if you want to adopt Bazel in the Python project, there's like a lot of work around just having rules that are made up. So like you just download those and you use them. And like you write like, I know, Py binary or Py library and it just compiles. You don't really have to build all of those implementations because they're already ready for you. And there's like adoption for, I think, all of the major languages.
So 2 questions.
Go on.
The first one about what you just said. One problem I found with Bazel is that it doesn't support cycles in dependencies, which Python does. Like this is a big problem. I think it's being worked on. I've been commenting on an issue there for Bazel, and somebody is working on it. I don't know. Like so, if somebody uses like Airflow, for example, like which I develop, it's like we have cycles, and that's a problem. But is there any problem with that in your environment? And secondly, in my distant past, I did a build system for Android, the OS.
Yeah.
Not the Android apps, Android
Yeah.
OS. And we managed to decrease the build from like 4 hours to 20 minutes for the whole system from the scratch by using TMPFS. Like instead of using on file system, of using the regular file systems and disks, we used like huge memory instances. Are you doing something like that?
So to answer your question, your first question, we do not support cycles. So essentially, if someone enters the cycle, they have to fix this, and that's it kind of works for us this far. For the second question, we do acknowledge that the I/O on file I/O essentially is like a major part of latency of a build, and that's why we do not run TMPFS. We run this for like the sandbox that we run. So like if you build something locally right now in CI or DevBox, it's going to run a sandbox and it's inside memory, right? So it's like a TMPFS system. However, all the files are actually living on like NVMe disks, right? But that's like, we are using NVMe to increase the performance.
So just a piece of advice. Because I managed not only to speed up the builds from 4 hours to 20 minutes, but also decrease the cost it needed because we run much bigger machines with lower disk, but bigger memory, but they took 8 times less time to run all the builds.
Yeah.
That might be that I found it especially for C, C++ and those parallelism and compilation. As the parallelism is good, but if you compile many different small files, the I/O becomes a really contention. And memory, TMPFS.
To repeat, essentially the build happens inside TMPFS right now. Like the sandbox that runs the build is inside TMPFS. It's just like the remote cache that stores persistent data is on NVMe, right? Because we don't want to lose it. Cool.
All
are we
right.
done?
Yeah, thank you very much. Great speech.
Thanks.
If you have any more questions, please ask them after the next speech.
I'm going to stay around for, probably like half an hour or so, so feel free to approach me if you have any questions.